Okay, so what our goals are now is to continue to fill out the table for percent recovery of ICV, percent recoveries of CCVs, percent recoveries of dilution, and then calculate percent relative difference for our table 1 information, and then do the same thing for the table 2 information to calculate the percent relative standard or recovery on a standard reference soil, percent relative standard deviation for our replicate, or sorry, for our duplicates. Yes.
My values for the MDL thing
Mhm.
are different because I have for the magnesium I have the 0.56 and the potassium I have 0.71 because on the spreadsheet they're kind of like flipped around.
Yes. Is that true for all you? So let's just assume that I made a mistake. 0.56. This one is 0.71. Okay. 71. Thank you. Okay, so let's go to our spreadsheet and we're going to calculate percent recovery of ICV. You know that we do or calculate a percent recovery of an ICV when? Initially, right? It's initial calibration verification. So after we calibrate and we have an R squared that has more than 3 nines on it, then we'll do an initial calibration verification. That is just checking the accuracy of the calibration. So it's using another standard material to create a standard that we compare to our original curve. Okay, so the place that we want to go for this information is the cations for ECEC instrument QC spreadsheet. And the way to calculate a recovery, remember? Say percent R ICV. It is measured over the known, right? Times 100%. Okay, so I'll just go ahead and calculate measured over the known, right? For these values that you have here. The known is given in column A, right? And the measureds are in columns B, C, D, and E. You know what I mean?
Can you say that again?
Yep. So my knowns are here, right? So the first ICV was 5 part per million. Second ICV was 20 part per million. The known or the measured are these ones here. Those, if they were all perfectly recovered, they'd be 5, right? So we need to figure out what the recovery is. And then for these, that would all be 20. So I'll just go ahead and do those calculations. And convert them to percents. And where you have the value, it just means that it was too either low or too high to fit on the standard curve, so we don't have a value for them.
So sorry, the measured is for 5 parts per million?
So the known is here, 5 or 20. So we have 2 ICVs. That's all.
What is the measured?
Measured is 4.76, NA 4.798, 4.731.
Oh, so the known is the matrix.
So the known is a standard that we created that was 5 parts per million in all of those elements. And then we ran that against our calibration, and these are the values that we got here.
Oh.
So measured is that, divided by known is 5.
Oh.
And then once you have that information, you can put that in your table, right? And again, we're just reporting ranges. High to low, or sorry, low to high. Fantastic. Yeah, we're good. No decimal place on the percent. Round to the nearest whole number. Okay, next one. If you're ready, are you ready? Next one is calculating the CCV. CCV happens every 10 samples. And the CCV is listed here. You can see in a couple places we have the like similar concentrations. So the CCV is just running the same the same standard after we've run 10 samples. All right, so what I can do actually is just take this stuff here and copy it. I'm going to take that block and copy it here. And I'm just going to change my label to CCV. CCV stands for Continuing Calibration Verification. Good for everybody. Because the CCVs again are 5 and 20, right? Same as the concentrations of our ICVs. So then just go through your spreadsheet and keep pasting that block of formulas in until you don't have them anymore. And then after you've done that, what you can do, which is what I'm going to do, is I'm going to have Excel calculate a min and a max for me, so I don't have to look at it and try and figure it out myself. And so that's just a min and a max formula that Excel can do for you. And when you do it, you'll need to hold down the control key and just click on every single one. If you hold on the shift key, I had trouble with that last time I tried to do that. So I don't know if that'll work or not. You could try it. Go that across. Then do the same thing with the max. And then those are the values again that you're going to put in your table, right? From high to low. Or sorry, I always say that, low to high. And the CCVs just tell us, like, as we're going through our run, is our calibration holding, and are we continue to measure accurately the elements that we're interested in measuring? And the answer now that we can say unequivocally is yeah. Because what's our desired performance level? Almost. So at the method level, that's what it would be. But at the instrument level, pretty much everything is always 90 to 110. And we have one value that's slightly below that, but not by much. Are you good? Not good? Good, but just need a little more time? That's what you mean?
How did you do the min and max again?
Good question. So what I did is this, I'll just do it over here so it's fresh. I clicked on the function and you can type in min if it doesn't come up, but you can just put in min and then you can click on the min, go min and you go okay. And then you hold down your control key and go up to the top and manually select just the ones for calcium. And then we're going to fill that across. But you got to keep your control key hold down because then it'll just take each of those cells and determine what the min and the max is. And the max is the same, right? It's just the max formula. Too bad. I'm just kidding.
So on the end of the spreadsheet, as we got to the bottom, why do we do the CCV at 5 ppm 2 times?
Good question. So the CCV was done a second time at the very bottom because there were some extra dilutions that I had the instrument chemist run that I put back up into the spreadsheet. I put those samples in a different place in the spreadsheet. Okay, good question. Are you ready to do the next one, or you want a little more time? A little more time? And just so you recall, the order of the elements is calcium, potassium, magnesium, sodium, but in the QC table, it's calcium, magnesium, potassium, sodium. So the magnesium and the potassium are just a little, just different or reversed. All right. Next thing we come to is percent recovery of diluted samples. Right. So percent recovery of diluted samples. Let's see. I think for that one, we need to look at our cations for ECEC tab because this is where we have some diluted data. And here we go. So, do your spreadsheets look like mine, pretty much? Yeah. All right. So you can see at the bottom of the very bottom of the spreadsheet, we have a dilution factor of 10 for a lot of these samples, and then some measurements for those. And then these equate to Los Osos, A and BT horizons, and the CR 5, 6, and 7 are not diluted. Those are just duplicates, so those are intermixed in there. And for our purposes, let's get rid of CR 5, 6, and 7 by just I don't mean anything personal about it. Right. we're just gonna simplify it. And then we got SRS 1506, SRS 1606, and the others. So those are diluted also 10 times. All right. Do you have something similar that as me? I'll make it bigger so you can see it actually. All right. Does yours look something similar to that? Yes.
I think it's possible that you deleted 54.
Oh, I changed the order, right? Right here. See that? Remember that? Change the order. Did you change the order? Okay. So change the order, and the one way to change the order is to insert a cell. So if you click above the place that you want to insert, actually, let me do this. Click where it says 50, and then right click and go to insert. That's not what I wanted. Delete that, sorry. And then just go to the place where you want to insert a cell. So I want to insert a cell here. So I can go insert and then move. So you can select all of this. Like if this is your situation here, you can select all of that and just drag it up. Does that make sense? So I want it to say SRS 1506 and then SRS 1606 and then again SRS 1506 and SRS 1606. And the reason why I want that is because in the other place where I have those values, it's in that same order. All right, so I'm going to delete it. Now, all right, so there is some other information. Like below, do you see all that? Like it says SRS information, stuff like that. You see all that? Let's just get rid of that too for right now, because we're not going to look at that. Delete it. So we have our Los Osos soil A and BT, and then we got SRSs that we diluted, and then we want to look at the places where we didn't have dilutions, right? So if I go up to the top of my spreadsheet, here are locations where for Los Osos I didn't dilute, right? For those ones, and then similarly, my SRSs are here, right? Where I didn't dilute. So I want to compare my sample to when I diluted it to when I didn't dilute it. Okay, and see if I recover my dilution factor back, in other words. Okay, so the formula that we're going to use is percent recovery of a dilution. And you have that information, and it looks like this. So you take your diluted sample, multiply it by the dilution factor, and divide that by your undiluted sample. Right? So diluted times dilution factor divided by undiluted, and see if we recover it. So if we go back to the spreadsheet, show you how it's going to go or how it's going to look. So I'm going to call this percent recovery of dilutions. Maybe I'll put that there. Percent. Percent recovery dilutions. So my diluted samples are here. So I'm going to say equals, and then I'm going to do that sample right there, which is diluted, times 10, because that's my dilution factor, divided by my undiluted sample. And this is Los Osos A number 1, right? So I'm going to go up to the top where I have Los Osos A number 1, and that's sample number 9, and just select that. And it's over, right? So don't worry about that. So we're going to click enter, and it's not going to be able to calculate it for us because we have a word in that calculation. So I'm gonna move that over like that. And then I'm gonna scroll down, but I'm only gonna scroll down how many? Just to here, right? So that's 8. The reason why I'm not gonna scroll down more is because then we get into the Costa Rica samples. And I need to reinsert my formula again when I get to the SRSs down here. Okay, so down here, I'm gonna go across like that and go 2, 3, 4, 5, 6, 7, 8. All right, and don't worry about where it says value yet. And then I'm gonna redo my formulas for the SRSs. Okay, so I'm gonna say equals SRSs start here. That times my dilution factor, which is 10, divided by the undiluted. And undiluted is here. Enter. I'm going to scroll across and then scroll down. 1, 2, 3. There we go. You good?
Nope.
Not at all. You want me to do it?
Scroll up to like which, so you have 43 to 57. and-
Yeah. So yours might be different, which is okay.
Oh, okay.
So these, I've isolated these because these are my diluted samples. So what I'm going to do is I'm going to say equals. So like if I inserted my formula again here, I can say equals this concentration, right? Because that's my diluted one. Yeah.
I'm not even at that point.
Okay. So where would you like me to go?
I'm just trying to get it organized so
Yeah.
that I can do
So
that.
you can do it. Okay.
So which soil should we be doing it on?
So the soils that you're going to do these on are the Los Osos A and BTs and the SRSs. So in total, you'll have 12 ones that we're going to do this calculation on. So what I'll do right now is and you can see that for calcium and for magnesium, or most of magnesium, we don't have any data. So I'm just going to get rid of those ones because they don't mean anything to us. And for magnesium, I'll get rid of the ones where we don't have any data. And then I'm just going to turn them into percents because that's what we want to present. And I think probably without doing a min and a max formula, you can probably figure out what they are, what the range is, right? So just figure out what the range is for calcium. We don't have data, so you can just put a NA in that cell. And then for potassium, just make sure that you and the person sitting next to you have the same thing. Same for magnesium, same for sodium.
One 126. Is that calcium? No, magnesium.
All right. You guys, you all good? You have the same values as me? I'm not saying I'm always right, because I do make mistakes, but. All right, are we good? Yeah, Liz. Good question. So the reason why we didn't get anything for calcium is because the undiluted samples were above our calibration range. So they're out of range, so we just don't have we don't have an undiluted measure. Yeah. Too high.
Oh, okay.
Too much calcium. It
Oh.
carbonate, yeah. Okay. So if we're good, we need to now calculate the percent relative differences. Right? Percent relative differences is just looking at replicate measures. So if we go back to our spreadsheet, and we're going to go to that tab right there, the cations for ECEC instrument QC thing. And you could see here as you scroll down that we did a replicate every 10 samples, right? We got a replicate there. We have a replicate here, and so forth and so on, right? We got all those replicates. However, we need to keep in mind places where our measures and our replicate measures are lower than our method detection limit, right? Because our method detection limit is the lowest limit that we can detect. So go back to this table here and just keep track of, let's see, keep track of, maybe write down what your MDLs are for each of the different ions, because we need to compare that to, to each of our measures for our replicates. And when I go back to my spreadsheet here, for calcium, it's 1.6. For magnesium, or sorry, for potassium, it's 0.71. And for magnesium, it's 0.56. And then sodium is 6.73, right? So then, if we look at this first replicate, right, we replicated measurement 6. And if we go up to measurement 6, right, those are original measures for running 6, and then I basically just reran number 6 again, right? That gives me a replicate value, but you can see that for sodium, they're below our ability to detect. So we're going to discount those values. That is to say, we're just going to omit them for sodium because they're too low for us to accurately detect. So the formula for percent relative difference, right? There's another formula, right? You've seen it before. And this is a measure, again, of precision. And so we'll go down and find that. Here it is. So when we only have 2 values that we're comparing to each other for precision, we use the percent relative difference formula. Percent relative difference is taking the absolute value of the difference of your repeat measures divided by the average of your repeat measures times 100%. Okay? So the difference divided by the average times 100%. You got it?
It's the absolute value that we're doing.
It's the absolute value. So to insert the absolute value right into Excel, you just type in equals ABS. Right, that'll determine the absolute value of whatever you have coming after it, and you're going to want to do some parentheses. Right, so I might do like the difference between whatever my cells are. I'm using Z1 minus Z2, and then that's going to be divided by my average Z1, or we'll just put in like average, right, of your Z1 and Z2, and then you're multiplying that whole thing, right, by 100%. Right? But we want to take the absolute value of the whole thing, so I'm going to put another parentheses all the way around the whole thing. Yeah. Give it a shot. And I'll give it a shot too. RD. I'm going to have it calculate sodium. I'm just not going to take that value. I'm just going to have it do it for all of them. And if you do it right, you should only have to do it once. Then you can take that, right? And you can paste it over and over again. However, you will have to change the cell that it's being compared to, right, every time. So in other words, are you ready for me to move forward? Be happy to. You see that?
What's the comma and the plus?
So I'm using, you can just have Excel calculate. Well, the difference between the comma and the plus is that the comma is saying that I have two values that that are not adjacent to each other, that I'm going to determine the average of.
Oh, so you're telling average.
Yeah, so I'm determining the average of this sample right here, and then I'm holding down the control key and then going up to sample 6 here.
Okay.
And clicking on that.
If you get 33, that's mean for you can do that with your slide part too.
And calcium, I got
54. I mean, not that it matters for calcium.
got 54, 14, 6. You think you might have one.
Yeah.
Okay, so we need to go back up here and all the values where either one of them is below the detection limit, we're gonna just get rid of it. And so for sodium, right, for this first set, they're below the detection limit, right? So I'm just gonna delete that. For the next set, I have value there and value there. That's because there wasn't a value that was measured. Probably because it was too high. Yeah, I think it was too high because it was over. And then sodium is 9.6 here. And then for sample 13, it's fine. So we can keep sodium there, right? The next batch, sodiums are less than our ability to detect. So I can get rid of that. What about, let's see, it goes calcium, potassium, magnesium. What about magnesium? No, they're all fine, right? All the other ones are fine. Our next batch. Oh, these are terrible. But it makes sense, right? Because every single one of these values is below our detection limit, right? All these right here, they're below. Calcium needs to be higher than 1.6. Potassium needs to be higher than 0.71. Magnesium needs to be higher than 0.56, and sodium needs to be higher than 6.73. So these are all just bad, right? I mean, we can't even measure those. So we can get rid of those. Whew, right? That's a relief. For these ones, same, right? They're not accurate either. Below the detection limit. These ones, sodium's below the detection limit. Everything else is fine. Whoa, look at that precision. All right, so go ahead and record that in your table. RD 7, 1 to 6, 1 to 11 should be less than 10%, right? Less than or equal to 10%. Okay, good. Fantastic. So then we go to our table 2, ranges of method quality control parameters. Percent recovery of an SRS and percent relative standard deviation. That's precision. So let's talk about percent recovery of SRSs. And I think that information is on cations for ECEC, I believe. Unless you're like me and you deleted it. Should be down here. You delete it also?
Yeah.
You moved it. Smart. But I'm not worried about it. So what I'm going to do is I'm going to email you a copy of the spreadsheet that's on Canvas or on OneDrive, okay? And it is called, I know that the numbers are out of order, but there's a reason for this. It is called 2023 CEC datasheet version 4, okay? In today's date, version 4, okay? So I'm going to email that to you right now. So I would suggest you close out the other one so you don't confuse yourself like I would if it was me. Shannon, you got another suggestion? Totally could, if you have your SRS data there. If you do, you're fine. You can just keep using that. All right, it's on the way. Okay, you good? Take that as a yes, you're good. So we have, let's see, at the bottom of the spreadsheet, we have SRS 1506 and 1606 and the known values in concentrations of milligrams per kilogram, right? And we did this twice. So I'm just going to take these values and copy them and paste them below also. Now, we need to calculate our SRS measured values, right? In order to compare. And the way that we're going to do this is that we're going to go back to our SRS values. Let's see, where are they? All right, so we got these ones up here that were undiluted. And then these ones down here, which were diluted. So I'm just going to use these diluted ones down here. Okay. So those are the ones I'm going to focus on. And all these concentrations are in milligrams per liter, parts per million, but in solution. And I need to convert them to parts per million in the soil, milligrams per kilogram. So in order to do that, I'm just going to use this as my example right here, 688. Actually, no, that's not what I'm going to use. I'm going to use this one, 7.65, because these are my knowns, right? So I don't need to worry about that. 7.65, which is SRS 1506 for calcium. So we got 7.65 milligrams of calcium per liter. And I want to convert that to milligrams of calcium per kilogram. So in order to go from a volume to a mass of soil, right? Because this is kilograms of soil. What do we need? What? That's close. Yeah, that's mass and a volume, right? So we need our soil to solution ratio. Right? Always soil to solution ratio. Anytime in the lab when we're doing calculations, you always will need your soil to solution ratio. Soil to solution ratio for this experiment. You don't remember it. It's in your lab notebook, I think. But it was 2.5 grams and 25 milliliters of solution, right? That was our soil to solution ratio. So we have 25 milliliters of solution over 2.5 grams of soil. And then I just need to make the units match. So I'm just going to say there's 1,000 grams per kilogram, and that gets rid of gram, and then there's 1,000 milliliters per 1 liter. Get rid of the milliliters, get rid of the liters, and it turns out that those cancel out. So this right here is just a factor of 10. Okay. Cancel out that. And this, right, when we do calculations like this, right, if you have your lab notebook with you, this would be a good type of thing to put in your lab notebook, right? Because this is related to our data. All right, just give it a clearly labeled heading for what it is you're doing. You're converting parts per million in solution or milligrams per liter, parts per million in the soil, milligrams per kilogram. Parts per million in solution, right? Because that's what we measured. And we want to convert it to parts per million in the soil. And the reason why we're doing that is because these concentrations that were given are in the soil kilogram. Now, the other thing is that this is a diluted sample. So we need to also multiply that by our dilution factor, right? Which was 10, right? So let's say 10, that is our dilution factor. So when you're plugging in the formula in Excel, you just take this number and you multiply it by 100. That's what your concentration of that sample was in the soil. Let's do that. So it's just whatever that value is times 100. And we can cross and fill it down. Bless you. Again, there's the formula right there. Okay. Okay. So if you have that, then to calculate the recovery, what do we do for recovery calculations? Over here. Right, this, here's what we measured. Next to it is the known, right? Here's what is known, that was given to us. Yeah, measured over known, right, times 100. That equals measured divided by the known. And multiply that, or make it a percent if it's not already a percent, and just fill it across. And sodium is crap. But that's okay. Why is it okay? I mean, it's okay. It's measured okay, but it's okay. Why? Yep. It's because, yeah, it's because all the measured values for sodium are below the detection limit. Right? The measured values in our diluted samples are like on the order of 0.5 to 0.7. And in the undiluted ones, we could go back up here, but those are even less than 6.73. So for sodium, right, all the values that we determined just then are below the detection limit. So they are inaccurate. They're inherently inaccurate. So I'm just going to get rid of them. We have one magnesium value that's really bad too. So that leads me to believe that there's maybe an issue with that one. Which one is that? That's the second SRS. It's this one. Those are all above the detection limit though. Oh, wait. Potassium, no, potassium's good. Okay, it's just bad. So then you just report the range again, right, in the table. Percent recovery of SRS. It's really bad. Oh, wait a second. It's potassium that's bad. You see what I did here? I juxtaposed, not juxtaposed, but I mixed them up. So this should be potassium. Magnesium. See that? Sorry. So our potassium's just bad. Why are they bad? They're all above the detection limit, though. Right. All right. So what this tells us is that at least in one of the SRSs, and I don't remember which one it was, the SRS 1506, we're not recovering, or actually, is that right? Yeah, SRS 1506, we're doing a really bad job of recovering magnesium. But in the other one, we did a good job, right? We recovered. So 1506 is where we have the 200s, right, percent recovery, but in the other one, we recovered it well. So that tells me that there's some issue with that standard reference soil, and I don't know what it is, but it doesn't tell me that we did a bad job at the experiment. Yeah.
So when there is like a 200% recovery, does that mean like there's extra potassium in it that we like they didn't think was in it when they did their original test?
No, it's on our end somewhere, because their samples have been rigorously analyzed by over 100 labs. So it's something on our end, and I don't know what it is.
Build potassium in the machine or something and a lot or something like that?
Yeah, it's probably not in the machine either. It's like our sample prep somewhere. Yeah.
I guess between, so like 124, so that would just be between 100 and one, like 80 and
120. Mm-hmm.
So if we're at like 124, is that okay?
It's okay, right? We desire 80 to 120. Those are our performance level standard, but it's just outside of that, right? So it's pretty good, right? But we can't make stuff up, right? That's why we report it. So we report what we got. If this was research work, I'd go back and try and figure it out and rerun the sample, try and figure out what's going on. But we don't have time to do that. So we're just reporting it as we see it. Okay. And based upon the fact that SRS 1606 is accurate, it's 118 to 121, which is right there within our performance level. I don't think there's a problem with the method. I think there was a problem with our analysis of that sample. Okay. And I'm confident in calcium. I'm confident in magnesium too, that we did a good job. Okay. So then what we have left is to calculate the percent relative standard deviation of our duplicate measures. So I'm going to go back to that same spreadsheet. And what I'm going to do here is just recall that all of my measures are done in quadruplicate, right? I got 4 measures of Stanislaus A, 4 measures of Stanislaus BT, 4 measures of Los Osos A, 4 measures of Los Osos BT. And then for my Costa Rica soils were done in triplicate, right? Costa Rica 1, 2, and 3 are duplicate measures of that soil. 4, 5, 6 are duplicate measures of that site, and 7, 8, 9, so forth. Okay, so what I need to do is remember what percent relative difference is. And percent relative difference is this formula. It's taking the standard deviation divided by the mean times 100%. Okay, so I'm going to do that. Let's do this. Okay, let's take cations for ECEC, and I'm going to do some more calculations on this, but I want to copy this and just put it right next to it. So to copy it, you probably know how to do it, but I have cations for ECEC selected. I'm going to right click on it and go to move or copy and click on the create a copy button. And it's going to go before the sheet. And I just want it to go before the sheet that's just below it, cations for ECEC instrument QC. See that? And click OK. Just make sure you check the create a copy button. Okay, and then it's going to come up with a number 2. And I'm going to double click on that and change the name. And I'm going to call this percent RSD calc. Okay. Next thing that I'm going to do is I'm just going to use these values up here to make it easier for myself. And you know that these are over. So what I will do is I'm going to do an equal in this cell right here. That's the first over for Los Osos A. You see that? I'm going to do equals, and then I'm going to go down and select the diluted Los Osos A, which is this one right here, and multiply that by 10. All right, so it should be 222 now. Yeah. So I got age 61 times 10. Yeah, it's just making it so I can do everything up here. So I'm gonna fill that down. And I'm gonna take this right here and copy it and paste it right here. And what that will do is it'll paste the formula, but move to the J column. And then I'm gonna copy that. Okay. I think that's all we need to do. So now for the percent relative standard deviation, we need the mean, we need the standard deviation and the mean for our 4 samples, right? Those. So what I'm going to do is I'm going to go to the last one, right? The last one within the set, right? And what I mean by that, the last one within the set is this spot right here. I'm going to type in percent RSD. And then above it, right here, I'm going to have Excel calculate the standard deviation. And then right here, I'm going to have Excel calculate the mean. And then here, I'm going to have it divide those. Okay. So click on your function, standard dev P, the one that I'm going to use. And click OK. And then my range of cells is the first 4 for calcium. Okay. Then I'm going to do the same thing for the mean or for the average. First 4. Then going to divide standard deviation by the mean. and multiply that by 100%. Or percent. That is standard deviation, H3 to H6. That is average H3 to H6. And then that is the standard deviation divided by the mean, which is the relative standard deviation. And then, like always, we're going to just fill it across. Like that. And then you can copy that block, right? And I would include the label for it too. Copy the block right there and paste it down to the next set. Right? But make sure that you leave one row and then paste it there. Leave one row, paste it there. Leave one row and paste it there. And that will do all of the Stanislaus and the Lososo soils. We need to do the same thing for the Costa Rica soils, but this time instead of having 4, we have 3. So we just need to adjust the formula. So I'm going to copy this formula again and just paste it right below the other one. And then I'll do it again, paste it right below for my Costa Rica soils, and I'll have to go back and adjust them. Here.
That's the.
Am I making the adjustment? That's an excellent question. So the way that I'm making the adjustment is for my standard deviation, it's H19 to H21. And for my average, it's H19 to H21. And then I can just fill it across. And I'll do the same thing for the next set. And so forth and so on.
For standard deviation, average.
Yep, because then the formula will be saved for relative standard deviation. And then what are you going to notice about your sodium data? Or is it too early to ask that question? I wasn't asking you, just kidding. Totally kidding me. I know. I'm just screwing around. And then if you're ready, you can have Excel calculate your min and your max if you want. We do. Just because it's part of our data analysis. And when we do deal with the Costa Rica soils, we've already done it. Right, so done. Are you ready to talk about the sodium data? Yeah. What's wrong with the sodium data? Like I'm looking at these values here. Most of them anyway. Below the detection limit, right? So there's only like one spot where they're not below the detection limit, but for the first set, they are below the detection limit. So I'm going to get rid of that. For the second set, they're below the detection limit. So I can get rid of that. For the third set, there's a couple that are below the detection limit. So I'm going to get rid of that. Fourth set is good though. Fifth set, Costa Rica A's are below the detection limit, most of them. Is that right? Yeah. And so is the other one. Actually, all the others are below the detection limit. Okay. So if we've all done it correctly, and I think that I have, but you check to make sure that yours match mine for your min and your max. That is our percent relative standard deviation. Fantastic. So you can copy that down and then report the range in your table. And I made the same mistake here, right? It's not calcium, magnesium, potassium. It's calcium, potassium, magnesium. How precise are our data? Should be less than or equal to 20%. Pretty good. Right? Pretty good. Okay, so that leaves us for our quality control calculations with some exchangeable acidity and some absorbed ammonium stuff, which we will come back to at a different time. How are you doing? You okay? Tired? I understand why. Can you push on a little bit more? Yeah, Chloe? Yes. Okay. All right. So let's do this. So we're back at our data here. And before we leave today, there's two things I like to talk about, and that is how to calculate a cation exchange capacity for the ECEC method. And I'd also like to talk to you about your lab notebook that you're going to turn in next week when you take your exam. So I'll give you, we'll save a little time at the end for that. Okay. So I'm on my cations for ECEC worksheet. And what I have, or what I'm looking at, is like all my data. And this spreadsheet is linked to some formulas over here that say sum of calcium, magnesium, potassium, sodium, etc. And right here, I have milligrams per liter and centimoles of charge per kilogram. Centimoles of charge per kilogram are cation exchange capacity units, right? So we're going to talk about how to convert milligrams per liter to centimoles of charge per kilogram. That's what we're going to do next. First thing, though, that we want to do is multiply, like we did before, multiply these values by their diluted sample times 10, just to put everything up in this area of the spreadsheet. So you did this already. We're just going to do it again. Okay, so I'm going to take that value and multiply it by that. It's 10. So you did all that before, no problem. Why? Good question. So the question was, why are we doing this? And the reason for that is, so when we calculate our amount of exchangeable calcium, magnesium, potassium, sodium, we're just going to do it at the top of this spreadsheet, right? So I'm just making all my data available at the top of the spreadsheet for convenience. This is for convenience. Okay. I'm just going to look through my spreadsheet now and see if there's anything else I want to do with it. And I don't. So here we're going to talk about how to convert milligrams per liter to centimoles of charge per kilogram. Notice in the worksheet, my labels up here, I did them wrong again. So it should be calcium, potassium, magnesium, sodium. Calcium, potassium, magnesium, sodium. So I am going to convert 69.08 milligrams per liter of calcium to centimoles of charge of calcium per kilogram of soil. That's what we're going to do. And this would be a good calculation to put in your lab notebook also, which is just going to be labeled something like conversion of milligrams per liter to centimoles of charge per kilogram, or cation exchange capacity. So the sample I'm going to use is this one right here, right, for calcium. Okay, 69.08. So we got 69.08 milligrams calcium per liter. And I need to convert that to centimoles of charge calcium per kilogram of soil. What do we need to do first? Always do this thing first, generally in lab calculations. Soil to solution ratio, right? Same soil to solution ratio as before, 25 milliliters, right? 2.5 grams soil, and we're going to convert this to kilograms and liters. So we have in 1 liter, we have 1,000 milliliters, and of course, in 1,000 grams, we got 1 kilogram. And so I can get rid of my grams and get rid of the 1,000 and get rid of the milliliters. Okay, so now I got milligrams of calcium per kilogram of soil, which is great for the denominator. But I need to convert milligrams of calcium to charge units now, or moles of charge. And if we have a mass of calcium, we want to convert it to moles of calcium. What do we need? Yeah, molar mass, right? And if you go to the periodic table, you'll know that for calcium, it's 40.08. So I'm just going to say this: 1 millimole of calcium is equal to 40.08 milligrams. Because I'm just keeping the units the same in the numerator and the denominator. It's the same as 1 gram per mole, or 40.08 grams per mole. Okay, so that gets rid of the milligrams. Now I have millimoles. I want centimoles. So 10 millimoles, 1 centimole. That cancels there. And then how many centimoles of charge are there in 1 centimole of calcium? 2 centimoles of charge. So for the other elements, it's the exact same formula or exact same dimensional analysis, except what's going to change is, so this was for calcium. For potassium, it's 1 millimole is 39, I think 0.01 milligrams. That sound right? And 1 centimole of charge, or 1 centimole. That sound right? Am I right, Zach?
For
Potassium,
potassium, 39.10 is what.
39.10. Okay, for magnesium, it's 1 millimole is 24,
31.
31 milligrams, and that is 2 centimoles of charge for 1 centimole. And for sodium, 1 millimole for 22.99 maybe.
Yeah.
Milligrams. And there's 1 centimole of charge for 1 centimole. So the calculations stay the same. Carrying across. We can simplify this formula a little bit when you plug it in to Excel. And that's here, right? That becomes 10. And that's actually get rid of that. And we get rid of that. So basically, it's just taking the quantity in solution, multiplying that by the charge, whatever the charge is, and dividing that by the mass.
Do you want us to do an example calculation of each one in our notebook?
If you just did it like this, that's fine. Okay, so go ahead and calculate these in centimoles charge per kilogram on your spreadsheet. I'll do the same. And we'll include the Costa Rica soils, but you don't need to do the SRSs because we already did them, right? We already figured out what the recoveries of those were. So I'm just going to stop right there. And the place that you can check to see if we are in agreement is in the sum R row R or column R, because that's going to add them all up. Oh. Don't worry about them. Because we calculated the recovery of those by converting them to milligrams per kilogram. So we don't need to know what the CEC is in centimoles charge per kilogram.